So very good afternoon to everyone. A very good evening to everyone. So I am Rohit Gehlot and I will be taking the week 10's material characterization tutorial. So firstly, in this week, basic introduction about the TM was discussed. So and majorly uh, all the major things are covered in the previous tutorial and in the lectures also. So I will be just giving a brief about them. So if anyone has any doubt, feel free to contact me. Okay. So firstly, we'll be talking about the electromagnetic lenses. So it can be seen that these are the it comprises some windings, and then these are the electrons when they pass through them. Then the electrons, as the electrons are charged, and therefore they get deflected whenever they cross the magnetic field. So therefore, as can be seen in the figure, these are the windings, and then there is a certain magnetic field is created in between this, and then when the electrons are passed, they get deflected. So the key to an understanding what is essentially a very simple lens is the direction of force which acts on a moving electron in a magnetic field. So this is the velocity vector of the electrons, and then this is the magnetic field vector. So the so the direction of the force is acts on a moving electron in a magnetic field. So this is the electron. So these are the electrons when they pass through this magnetic field. Then there are the two vectors, radial and the longitudinal, and then uh, so the angle between. So if an electron E, which is moving with velocity v, experiences a magnetic field of strength B, then it suffers a force of F is BeV in a direction perpendicular to the both the direction of motion and the magnetic field. So typical electromagnetic lens is designed to provide a magnetic field almost parallel to the direction of the travel of the electrons. This is very important thing. So whenever we design a magnetic field for any kind of instrument like TM, so a magnetic field almost parallel to the direction of the travel of the electrons is designed. So an electron entering the lens experiences a magnetic field B, which can conveniently be resolved into components BAX along the axis of the microscope and B radial in radial direction. So these are the two components of the magnetic field. AX is along the axis of the microscope, and B radial is the in a radial direction. Okay. So initially the electron's movement is not affected by B axial, which is parallel to the direction of the travel. So but it experiences a small force B radial to EV due to radial component. This causes electron to travel in a helix along the lens. Okay, so as soon as the electrons start to spiral, it has a component of velocity v circumference perpendicular to the plane of the paper. So v circumference experiences a force B axial EV circumference in a radial direction. Okay, so thus the helical path follows a tighter and tighter radius, and effect is that a parallel beam of electrons entering the lens is caused to converge to a point exactly as light is focused by a glass lens. So if a magnetic field extends over a short distance along the axis, the lens behaves as a thin lens, and all the geometrical expression for thin glass lens apply for this. So a current of 0 greater to 1 ampere apply in the coil, wherein the current can vary the focal length of the lens. Okay, so the electromagnetic lenses works at a fixed focal length, fixed focal distance, and variable focal length. So by fixed focal distance mean that the distance between the subject you are focusing to the camera sensor, while the variable focal length means the distance from the center of the lens to the principal foci or focal points of the lens. So like the human eye lens, but unlike light optics. So simple rheostat can vary power of the lens, varies current. So electrons are also spiral through lens effect easily observed. So till now, anyone has any doubt, feel free to ask. Okay. So the transmission electron microscope, so it uses a stack of lenses. These are the condenser lenses. So generally it utilizes two condenser lenses to spot onto specimen. 2 plus micrometer diameter, so it focuses and also then a short focal length of around 2 mm, high powered objective lens to image the object, and then the longer focal length intermediate lenses to enlarge the final image, which is projected onto a fluorescent screen. If we talk about the condenser system, so the Vanat cap focuses the focuses to a crosser which is accelerated down the column. So this is these are the condenser lens 1, condenser lens 2, then this is the condenser aperture, and then this is the illumination angle, and there is the specimen. Okay, so the first condenser C1 demagnifies crossover to give a smaller point source. This is referred to as spot size. The second condenser lens C2 is used to either converge or spread the beam of illumination on the sample. This is your Vanat cap. It focuses the beam to a crosshair which is accelerated down the column. So it focuses. Then the first condenser C1, it demagnifies the crossover to give a smaller point source. Okay, so this is referred to as a spot size. Okay, then the second condenser lens C2, is used to either converge or spread the beam of illumination on the sample. Okay, then a condenser aperture is placed in the beam path to remove electrons far from the optic axis, which would reduce resolution. So the smaller the aperture, the better the resolution, but there is an associated decrease in brightness, therefore there is a need of compromise. So condenser aperture is placed in the beam path to remove electrons far from the optic axis, which okay. So overall, the rotation of image occurs due to the spiral movement of electron beam. Cunning design of electron optical system in modern microscope involves correction of this image rotation effect. Now if you talk about the wavelength of the electrons, then it can be taken as the q dot u is equal to half mv square, where lambda is h by mv. So from these two relations we can find out the lambda as 1.23 nanometer times divided by u root u, and lambda is h by p. So we can calculate it as h by root 2m eu plus eu by c square. Okay, so now we talk about the TEM. So the instrument components, it involves then the electron gun, then condenser system, it comprises lenses and aperture for controlling illumination on the specimen, then the specimen chamber assembly, followed by objective lens system, projector lens system. So this is the hairpin cathode, hairpin like cathode, then this is the Van cylinder, then these are the anode, then followed by condenser lenses with the condenser aperture of around 100 to 400 micrometer, and here is your specimen. Then comes the objective lenses. These are the diffracted beam. So the objective back focal plane, also plane of the diffraction pattern and of the objective aperture diaphragm. Single stage magnified image, also plane of the reflected aperture diaphragm. Then comes the intermediate lenses. These are the intermediate lenses. Then intermediate A, two stage magnified image. In B, diffraction pattern image in one state, also plane of the intermediate scheme. So then followed by this projective lens, and here comes in a three stage magnified image, two stage magnified diffraction pattern, final screen or photographic plate respectively. So now these are the different abbreviations, like HEED is used for high energy electron diffraction, LWM is used for low energy electron microscope, energy electron energy loss spectroscopy, energy dispersive X-ray spectroscopy, and then followed by electron scanning electron microscope. Electron do not normally transmit the sample. Okay, so now if you talk about the difference between the kV and kilo electron volt, so with kV is meant the high voltage. So if an electron was accelerated in this electric field with an example around 20 kV, the electron has finally an energy of 20 kilo electron volt. So for SEM, the acceleration voltage is the high voltage applied to the filament, and the acceleration voltage ranges from 100 volt to 70 kilovolt. Low acceleration voltage means less than 1 kV. Now, if we talk about the optics of the TEM, so the comprises guns, lenses, apertures, and screen. So then these are the electron source interaction which we already discussed. So transmitted beam generally utilized for the TEM. So it is generally utilized for high resolution images, submicron level diffraction, defect imaging, dislocation, twin stacking fault, point defect, antiphase boundaries, simultaneous imaging, structural and compositional analysis, orientational studies, possible identifying the phase and crystal structure and site occupancy of atoms. So time diffraction, what can we infer? So phase and crystal structure type, crystal symmetry and space group, orientational relationship between phases,